Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home on your commute or winding down for the evening, I'm really glad you're here. Now, I want you to try something with me. Close your eyes for just a moment, or if you're driving, just imagine this really vividly. Picture yourself floating in absolute darkness. Not the darkness of your bedroom at night, not even the darkness of a cave deep underground. I'm talking about the kind of darkness that exists between galaxies, where there's literally nothing around you for millions and millions of miles. You're floating there, and suddenly you start moving. Not walking, not flying, you're traveling at the speed of light, 670 million miles per hour. At this speed, you could circle the Earth 7.5 times in just 1 second. You travel like this for 1 billion years. Think about that for a second. 1 billion years. Every civilization that has ever existed on Earth, every dinosaur that ever lived, every mountain that ever formed and eroded away, all of that would happen 1,000 times over while you're racing through this cosmic darkness. But you keep going. Another 1 billion years pass, then another. 13 billion more years flash by as you hurtle through space at light speed. You've now been traveling for 15 billion years total. You've covered a distance so vast that there isn't really a good way to comprehend it. You've traveled farther than the distance to the most distant galaxies we can see with our most powerful telescopes. And then you hit something. What could it possibly be? A wall? Some kind of cosmic barrier made of energy or matter we can't even imagine. Do you just stop, like you've bumped into an invisible force field? Or maybe there's nothing there at all. Maybe you just keep going forever and ever, through endless, empty darkness that never, ever ends. Here's what's absolutely mind-bending about this thought experiment. This isn't just some fun imagination game. This is the most fundamental question that human beings can ask about reality itself. Does everything that exists, every star, every planet, every atom, every bit of empty space between them, does all of that have a boundary? Does the universe have an edge? Now, I know what you're thinking. You're probably thinking, well, of course it has to end somewhere, right? Everything ends somewhere. But here's the thing that's going to make your brain hurt in the best possible way. What if it doesn't? What if space just goes on and on and on, literally forever? And if it does end somewhere, what's on the other side of that ending? Think about it like this. Imagine you're in your house right now, and you walk to the wall and you push against it. On the other side of that wall, there's either another room, or the outside world, or your neighbor's house. There's something there. But what if you could somehow walk to the edge of all existence itself? What would be on the other side of that wall? More space? Nothingness? Something completely beyond our ability to even imagine? This question has been this one simple question about whether space has an edge, has been driving human beings absolutely crazy for as long as we've been able to look up at the night sky and wonder what's out there. From the moment our earliest ancestors first looked up at the stars scattered across the darkness, we've been haunted by this possibility. We've been asking, where does it all end? And the crazy part is, we still don't know for sure. Even now, in 2025, with all our technology, all our telescopes, all our mathematical equations that can predict the behavior of black holes and the birth of stars, we still don't know if the universe has an edge. But here's what's absolutely fascinating. We're closer to an answer than we've ever been before, and the journey to get to this point, it's one of the most incredible detective stories in history. Let me tell you about the people who've been wrestling with this question. 65,000 years ago, oh so 65,000 years ago, the Aboriginal Australians were mapping this question into what they called songlines. These were oral maps passed down through generations that described not just the landscape of Australia, but the very structure of reality itself. They understood that the question of where everything ends was also the question of where everything begins. Jump forward to 2,500 years ago in ancient Greece. Brilliant minds like Aristotle and Archytas were having heated debates about this exact same question. Archytas came up with what might be the perfect way to think about this problem. He said, "Imagine you're standing at the very edge of the universe. You stretch out your arm and try to extend it beyond that edge. What happens? Does your arm just stop? Does it hit something? Or can you keep extending it, which would mean there's more space beyond what you thought was the edge?" This question is so fundamental that it's like asking, what is existence itself? Because if space has an edge, then what defines that edge? And if space doesn't have an edge, then how can something infinite even be real? Here's where it gets even wilder. Just last night, literally just last night, the James Webb Space Telescope, that incredible machine we've got stationed nearly 1 million miles from Earth, was peering 13 billion years into the past. 13 billion years. It's looking at light that started traveling toward us when the universe was just a baby, less than 1 billion years old. But even seeing that far back in time, even looking at galaxies that formed when the cosmos was still figuring out how to make stars and planets, we still can't see the edge. We can see what we call the observable universe. That's everything that light has had time to reach us from since the beginning of time. But beyond that, we just don't know. And right now, as I'm talking to you, there's a physicist in Geneva, maybe sitting in a coffee shop or standing in front of a whiteboard covered in equations, running calculations that might finally give us the answer. There are teams of scientists using some of the most sophisticated instruments ever built, measuring the way space itself is shaped, trying to figure out if we live in a universe that goes on forever, or one that eventually loops back on itself like the surface of a sphere. Now, you might wonder why this matters. I mean, it's not like you're planning to travel to the edge of space anytime soon, right? But here's the thing. This question touches absolutely everything about what it means to exist. If the universe is infinite, then somewhere out there, mathematically speaking, there has to be another version of you. In fact, there have to be infinite versions of you. There's a version of you who decided to listen to a different podcast today. There's a version of you who never learned to read. There's a version of you who became an astronaut and is floating in a space station right this very moment, also wondering about the edge of space. But if the universe has an edge, if there's a boundary to all existence, then that changes everything. It means we truly are alone in all the emptiness. It means that every thought you've ever had, every decision you've ever made, every moment of joy or sadness or wonder you've ever experienced, all of that is the only time those exact things have ever happened in all of reality. Think about that for a moment. Every laugh you've shared with a friend, every time you've watched a sunset and felt that little tingle of awe, every moment when you've suddenly understood something that confused you before, if the universe has edges, then those moments are absolutely unique in all of existence. They've never happened before, and they'll never happen again anywhere else in all of reality. But we're not just talking about philosophy here. This isn't just some abstract question that doesn't affect the real world. The shape of space, whether it's infinite or finite, whether it has edges or curves back on itself, that determines the ultimate fate of everything. Every star that's shining right now, every planet that might have life on it, every galaxy spiraling through the cosmic dark, their future depends on the answer to this question. If space is infinite and flat, stretching on forever, then eventually all the stars will burn out, all the black holes will evaporate, and everything will fade into a cold, empty darkness that goes on forever. But if space curves back on itself, if the universe is like the surface of a four-dimensional sphere, then maybe time itself loops back around. Maybe the end becomes the beginning. And here's something that's going to blow your mind. We might not be the only universe. There might be infinite other universes, each one like a bubble floating in a vast cosmic foam. Some of those bubbles might have completely different laws of physics. In some of them, gravity might work backwards. In others, there might be 17 dimensions instead of the 3 we're used to. Some of them might be so alien that the very concept of matter and energy and time works in ways we couldn't even begin to imagine. Scientists call this the multiverse, and if it's real, then our entire universe, with all its hundreds of billions of galaxies, all its countless stars and planets and potential life forms, our entire universe, might just be one tiny bubble among infinite bubbles, each one containing its own version of reality. But here's what gets me really excited about all this. We're living at the exact moment in human history when we might finally get answers to these questions. For thousands and thousands of years, humans could only wonder about the edge of space. We could philosophize about it. We could create myths and stories about it, but we couldn't actually investigate it. Now we can. We've got telescopes that can see almost to the beginning of time. We've got equations that describe how space bends and curves. We've got computers that can simulate the evolution of entire universes. We're sending spacecraft to the outer reaches of our solar system, and someday we'll send them to other stars. And the most amazing part? The tools we're using to explore these cosmic questions are helping us understand everything else too. The same mathematics that describes the shape of space also helps us build GPS satellites that know exactly where you are. The same technology that lets us peer billions of years into the past also helps doctors see inside your body without surgery. When ancient humans first looked up at the stars and wondered where it all ends, they couldn't have imagined that their descendants would build machines capable of detecting gravitational waves, two ripples in space itself created when black holes collide. They couldn't have imagined that we'd figure out how to split atoms and harness the same force that powers the stars. They couldn't have imagined that we'd create a worldwide network that lets any human being access the sum total of human knowledge instantly. But all of those incredible achievements started with the same question that's been haunting us for 65,000 years. What's out there? Where does it all end? What lies beyond the furthest thing we can see? And now, for the first time in human history, we're on the verge of actually answering that question. Not with guesses or philosophy or beautiful myths, but with observations and measurements and mathematical proof. The journey we're about to take together is the story of how human beings went from standing under the night sky, wondering what those little points of light could be, to building machines that can detect the afterglow of creation itself. It's the story of how we went from thinking the Earth was the center of everything, to discovering that we're on a small planet, orbiting an ordinary star in an ordinary galaxy that's just one of hundreds of billions of galaxies scattered across space. But most importantly, it's the story of how we're about to find out whether everything that exists has a boundary, or whether reality itself goes on forever and ever, unlimited and infinite, and completely beyond our ability to ever fully explore. So buckle up, because we're about to dive deep into the most mind-bending, reality-challenging, absolutely fascinating question human beings have ever asked. We're going to travel from ancient Babylon to modern particle accelerators, from Aboriginal songlines to space telescopes, from the equations of Einstein to the most cutting-edge theories about quantum gravity and cosmic inflation. And by the time we're done, you're going to see the universe, and your place in it, in a completely different way. You're going to understand why this question about the edge of space is really a question about the nature of existence itself. Because here's the beautiful, terrifying, absolutely incredible truth. We live in a universe so vast and so strange that our brains, evolved to navigate the African savanna and recognize faces and avoid predators, can barely even begin to comprehend it. But somehow, miraculously, those same brains have figured out how to ask the right questions and build the right tools to actually get answers. The edge of space isn't just about space. It's about time, it's about consciousness, it's about what it means to be human in a cosmos that's either infinitely large or mysteriously bounded. And that story, Norma, that incredible, mind-expanding, reality-redefining story, starts with a simple question that breaks our everyday understanding of what's possible. What happens when you travel as far as you can possibly go? Picture this. It's 4,000 years ago, and you're standing at the top of a massive ziggurat in ancient Babylon. These aren't just buildings. They're artificial mountains made of millions of baked bricks, rising 200 feet into the desert sky. You're a priest, and you've climbed all the way to the top because you believe, you absolutely know, that if you reach high enough, you can almost touch the solid dome that holds back the cosmic waters above. From up here, you can see for miles across the Mesopotamian plain. The Euphrates River winds like a silver ribbon through green farmland, and beyond that, the world fades into hazy desert. But in your mind, you can see much farther than your eyes allow. You've got the whole cosmos mapped out, and it makes perfect sense. The Earth, you know, is a flat disk floating in an endless ocean. At the very edge of this disk, where the land meets the primordial waters, that's where the sea monsters dwell. Massive creatures with the power to shake the foundations of the world itself. And above everything, above the land, above the monsters, above the waters, there's a solid dome made of some kind of divine metal or crystal. The stars? They're just holes poked in that dome, letting through tiny bits of the blazing light from the realm of the gods. Now, here's what I find absolutely fascinating about this. These ancient Babylonian priests weren't primitive or naive. They were sophisticated mathematicians and astronomers. They could predict eclipses. They tracked the movements of planets with incredible accuracy. They invented the 60-minute hour and the 360-degree circle that we still use today. But when it came to the ultimate question, where does everything end? They came up with this beautiful, terrifying vision of a bounded cosmos surrounded by chaos. And they weren't alone. Jump across the world to ancient India, and you'll find Sanskrit texts describing something completely different but equally mind-bending. The universe, according to these texts, wasn't a single disk floating in water. Instead, it was infinite. Golden eggs, countless perfect spheres floating in infinite darkness. Each egg contained its own complete universe, with its own gods, its own version of Earth, its own stars and planets. Think about that for a second. 4,000 years ago, people in India were imagining infinite parallel universes. Each golden egg was like what we might call a bubble universe today, a complete, self-contained reality floating in an endless cosmic void. And here's the wild part. This infinite darkness that contained all the golden eggs, it had no beginning and no end. It just was, forever and always. Meanwhile, halfway around the world, the Maya were developing their own incredible vision of cosmic boundaries. But for them, the universe wasn't static at all. Instead, it regenerated itself in vast cycles. Every 5,125 years, everything would end and begin again. Not just civilizations or empires, everything. All of space, all of time, all of existence would complete one great cycle and start fresh. Picture the Maya priests standing atop their pyramid temples in the rainforests of Central America, calculating these cosmic cycles with mathematical precision that wouldn't be matched in Europe for another 1,000 years. They knew exactly when the current universe had begun, and they knew exactly when it would end and restart. To them, the question wasn't whether the universe had boundaries, it was how many times those boundaries had already been redrawn. But here's where things get really interesting. While these different civilizations were developing their cosmic maps in isolation from each other, they were all grappling with the same fundamental problem. If you travel far enough in any direction, what do you eventually hit? And each culture's answer revealed something profound about how they understood reality itself. The Babylonians, living between two great rivers in a fertile but isolated valley, imagined a cosmos that was fundamentally safe and bounded. Yes, there were monsters at the edges, but those edges existed. There was a solid dome overhead protecting them from the chaos beyond. Their universe had clear limits, clear structure, clear divine order. The Indians, living in a vast subcontinent that seemed to stretch endlessly in every direction, imagined infinite space filled with infinite possibilities. Their cosmos had room for every possible version of reality, every possible way things could be. The Maya, living in dense rainforests where the cycles of growth and death and rebirth were visible everywhere you looked, imagined a universe that died and was reborn in endless succession. Their cosmos was all about transformation, about the fundamental impermanence of everything that exists. But then, something happened that changed everything. Around 2,500 years ago, in the Greek city-states scattered across the Mediterranean, a new kind of thinking emerged. Instead of just accepting traditional cosmic maps passed down from their ancestors, Greek philosophers started asking a different kind of question. What can we actually prove about the shape of space? And that's when this whole investigation took a completely different turn. A philosopher named Archytas came up with what might be the most elegant thought experiment in human history. He said, "Imagine you're standing at the absolute edge of the universe. You've traveled as far as it's possible to travel. You're at the boundary where everything that exists meets, whatever lies beyond. Now, stretch out your hand. Try to extend it past that boundary. What happens? If your hand hits something solid, then that solid thing is part of the universe, which means you weren't really at the edge after all. There's more space beyond what you thought was the boundary. But if your hand doesn't hit anything, if you can extend it freely, then again, there's more space beyond the supposed edge. Either way, you haven't found a true boundary." This is absolutely brilliant, right? With just logic and imagination, Archytas had identified a fundamental paradox. Any boundary to space implies more space beyond that boundary. It's like trying to find the edge of a piece of paper by drawing a line on it. The line itself takes up space, which means there's paper beyond the line. But Archytas's contemporary, Aristotle, wasn't satisfied with this kind of abstract reasoning. He wanted to figure out what the cosmos actually looked like, not just what it logically had to be. And Aristotle came up with his own cosmic vision that would dominate Western thinking for the next 2,000 years. According to Aristotle, the universe was a perfect sphere with Earth at the center. The moon, sun, planets, and stars were all mounted on crystalline spheres that rotated around Earth in perfect circles. And beyond the sphere that held the farthest stars, absolutely nothing. Not empty space, not darkness, not even a void. Just nothing. The absence of existence itself. Now, this might sound primitive to us today, but think about what Aristotle was actually proposing. He was saying that space itself has a shape, a spherical shape, and beyond that shape, there's no space at all. It's not that there's empty space beyond the star sphere. It's that the concept of beyond doesn't even apply. It's like asking what's north of the North Pole. The question itself doesn't make sense because you've reached the limit of what the concept of direction can describe. This idea that space itself could have a shape and a boundary was so radical that it broke people's brains for centuries. Common sense tells us that if something has a boundary, there has to be something on the other side of that boundary. But Aristotle was suggesting that space itself could end without there being any other side. And here's what's absolutely wild. Modern physics has circled back to something remarkably similar to this ancient Greek insight. Today, we talk about curved space-time and closed universes, and the possibility that space could be finite but unbounded, exactly what Aristotle was trying to describe 2,400 years ago. But I'm getting ahead of myself. Let's stay in the ancient world for a moment. because the Greeks weren't done revolutionizing our understanding of cosmic boundaries. A few centuries after Aristotle, a mathematician named Apollonius started thinking about infinity in a completely new way. Instead of asking whether space was infinite or finite, he started asking, what if both answers are true at the same time? What if space is infinite in some directions but finite in others? He developed mathematical techniques for understanding curves that stretched to infinity, what we now call hyperbolas and parabolas. And while he was working on these mathematical curves, he started to realize that space itself might be curved in ways that our everyday experience couldn't detect. Imagine you're an ant walking on the surface of a balloon. From your ant perspective, the surface seems flat and potentially infinite. You can walk in any direction and never hit a wall or boundary. But from outside the balloon, we can see that the surface is actually curved and finite. The ant is living in a two-dimensional space that's curved through a third dimension it can't perceive. Apollonius wondered, what if we're like ants on a cosmic balloon? What if our three-dimensional space is actually curved through some higher dimension that we can't directly experience? If so, then space could be both infinite from our perspective, we could travel forever without hitting a boundary, and finite from some higher dimensional perspective. This insight wouldn't be fully developed until Einstein came along 2,300 years later, but the seed of the idea was planted right there in ancient Greece. Meanwhile, other Greek thinkers were taking Archytas's paradox and running with it, in a completely different direction. A philosopher named Lucretius argued that the universe had to be infinite, not because of logical paradoxes about boundaries, but because of something much more practical, the nature of atoms. Lucretius believed that everything was made of tiny, indivisible particles moving through empty space, and if atoms are constantly moving and combining in new ways, then given infinite time, they would create infinite variety. Somewhere in the infinite cosmos, there had to be another Earth, another version of you, infinite worlds with infinite possibilities. Sound familiar? Lucretius was essentially describing what we now call the multiverse, OPI, the idea that our universe might be just one of infinite universes, each one exploring different possibilities of how matter and energy can arrange themselves. But here's what I find most remarkable about all these ancient investigations into the edge of space. Every single culture, every single philosopher, every single tradition was really asking the same question. What does it mean to exist? If space has boundaries, then existence itself has limits. Everything that is, everything that ever was, everything that ever could be, all of it, fits within some cosmic container. But if space is infinite, then existence has no limits at all. Every possibility, no matter how strange or unlikely, happens somewhere in the infinite expanse. The Babylonian priests, standing on their ziggurats, the Indian sages describing infinite golden eggs, the Maya calculating cosmic cycles, the Greek philosophers wrestling with logical paradoxes, they were all trying to understand their place in reality. They were asking, are we part of something bounded and comprehensible, or are we part of something infinite and ultimately mysterious? And amazingly, we're still asking the exact same questions today. We've got better tools now, telescopes that can see billions of light years, equations that describe the curvature of time, space-time, computers that can simulate the evolution of galaxies. But the fundamental mystery remains exactly the same. Does everything that exists have an edge? And if so, what lies beyond that edge? If not, how can something infinite be real? These ancient cosmic investigators didn't have particle accelerators or space telescopes, but they had something just as powerful, the ability to think clearly about the deepest questions reality has to offer. They looked up at the night sky with naked eyes and minds uncluttered by preconceptions, and they saw patterns and possibilities that we're still exploring today. The journey from those ancient ziggurats to modern cosmology is one of the most incredible intellectual adventures in human history, and as we'll see next, the real revolution was just about to begin. Because while the ancients could think about the edge of space, they couldn't actually observe it. That would require tools and insights that wouldn't emerge for another 1,000 years. But when they did emerge, they would shatter every assumption about cosmic boundaries that humans had ever made. The year is 1584, and a Dominican friar named Giordano Bruno stands in a palace in Rome, surrounded by 8 of the most powerful cardinals in the Catholic Church. These men have the authority to decide who lives and who dies, who speaks truth and who spreads heresy. And right now, they're asking Bruno to renounce the most dangerous idea anyone has ever conceived. Bruno looks each cardinal in the eye and refuses. What was this idea so threatening that the Church was willing to burn a man alive for it? Bruno believed that space was infinite, not just big, not just larger than anyone had imagined, but literally infinite, filled with infinite stars, infinite worlds, infinite possibilities for life and intelligence. Every star in the night sky, he claimed, was like our sun, surrounded by its own family of planets, and on those planets there might be other beings, other civilizations, other versions of humanity spreading across the cosmic vastness. For 16 years, the Inquisition kept Bruno imprisoned, trying to break his will, trying to get him to admit that the universe was finite and bounded, safely contained within God's perfect design. Bruno never wavered. On February 17th, 1600, they tied him to a stake in the Campo de' Fiori in Rome and burned him alive. But here's the incredible thing. Bruno's vision of infinite space filled with infinite worlds wasn't based on telescope observations or mathematical proofs. The telescope hadn't even been invented yet. Instead, Bruno had arrived at this cosmic revelation through pure philosophical reasoning, building on the ancient insights of Lucretius and pushing them to their logical extreme. If space was infinite, Bruno argued, then matter had infinite room to arrange itself, and if matter had infinite room and infinite time, then every possible arrangement would eventually occur. Somewhere in the infinite cosmos, there had to be another Earth. Somewhere, there had to be another version of you. Somewhere, there had to be infinite versions of everything that could possibly exist. The Church understood exactly what this meant. If Bruno was right, then Earth wasn't special. Humans weren't special. The entire cosmic drama of creation and salvation was just one tiny story playing out among infinite stories in infinite space. It was perhaps the most radical threat to religious authority that anyone had ever conceived. But Bruno's ideas didn't die with him. They spread like wildfire through the underground networks of European intellectuals. And just 9 years after Bruno's execution, a young Italian mathematician named Galileo Galilei heard about a remarkable new invention from the Netherlands, a device that could make distant objects appear much closer. In 1609, Galileo built his own version of this spyglass, improving its magnification to about 20 times normal vision, and then he did something that changed human history forever. He pointed it at the night sky. The first thing he looked at was the moon. Through his crude telescope, Galileo could see that the moon's surface wasn't smooth and perfect as everyone had believed. Instead, it was covered with mountains and craters, rough and rocky just like Earth. The celestial realm wasn't made of some perfect divine substance after all. It was made of ordinary matter, following ordinary physical laws. But that was just the beginning. When Galileo turned his telescope toward Jupiter, he saw something that shouldn't have been possible according to everything humanity thought it knew about the cosmos. Jupiter had 4 tiny points of light moving around it in regular orbits. Jupiter had moons. Think about what this meant. For 2,000 years, ever since Aristotle, everyone had believed that everything in the heavens revolved around Earth. The moon orbited Earth, the sun orbited Earth, The planets and stars all wheeled around Earth in perfect circles. Earth was the unmoving center of all creation. But here was Jupiter, clearly not orbiting Earth, with its own family of moons orbiting around it. The Earth-centered universe had just been shattered by 4 tiny dots of light that you needed a telescope to even see. Galileo was smart enough to know that this discovery would get him in serious trouble. So he wrote about his findings in code, in letters to friends, in carefully worded scientific papers that danced around the obvious implications. But the implications were unavoidable. If Jupiter had moons, then Earth wasn't the center of everything. And if Earth wasn't the center of everything, then maybe Bruno had been right about infinite space filled with infinite worlds. The cosmic bubble that had contained human imagination for thousands of years was starting to burst. But it was another Italian, working a few decades later, who really tore that bubble wide open. Isaac Newton wasn't content to just observe the heavens through a telescope. He wanted to understand the mathematical laws that governed everything in the universe. And when he worked out his law of universal gravitation, he stumbled into a paradox that nobody had seen coming. Here's the problem Newton discovered. If space is infinite and filled with an infinite number of stars, then the gravitational pull from all those stars should be infinite in every direction. Every single particle of matter in the universe should be experiencing infinite gravitational force, pulling it in every direction simultaneously. The entire cosmos should either collapse instantly into a single point or tear itself apart with infinite violence. But obviously, that's not happening. The stars are still shining, the planets are still orbiting peacefully. You're still sitting wherever you are listening to this story. So what was wrong with Newton's calculation? Newton himself was deeply troubled by this paradox. He spent years trying to solve it, coming up with increasingly elaborate explanations for why infinite gravity didn't destroy everything. Maybe the stars were arranged in some special pattern that perfectly balanced all the gravitational forces. Maybe God was actively intervening to keep the universe stable. Maybe space wasn't actually infinite after all. This problem would later be called Olbers' paradox, after the German astronomer Heinrich Olbers, who formulated it most clearly in 1823. But Olbers added another devastating insight to Newton's gravitational puzzle. If space is infinite and filled with infinite stars, then why is the night sky dark? Think about it this way. Look up at the night sky tonight. In every direction you look, your line of sight should eventually hit a star, somewhere out there in infinite space. It might be a very distant star, and its light might be very faint by the time it reaches you, but there should be a star there. And if there are infinite stars in infinite space, then every single point in the night sky should be blazing with starlight. The night sky should be as bright as the surface of the Sunday, but it's not. There are dark spaces between the stars. Olbers' paradox suggested that maybe space wasn't infinite after all. Or maybe there weren't infinite stars. Or maybe something was fundamentally wrong with our understanding of how light and gravity work on cosmic scales. These weren't just abstract philosophical problems anymore. They were mathematical contradictions that demanded answers, and those answers would require a complete revolution in how humans understood space, time, matter, and energy. That revolution began with a discovery that nobody saw coming. In the mid-1800s, scientists were trying to figure out the nature of light. They knew light was some kind of wave, but waves need something to wave through. Ocean waves move through water, sound waves move through air, but what did light waves move through? The answer, they decided, was something called the ether, an invisible, weightless substance that filled all of space and allowed light to propagate from stars to Earth. The ether was supposed to be the cosmic medium through which all electromagnetic phenomena traveled, but when scientists actually tried to detect this ether, they couldn't find it. Albert Michelson and Edward Morley designed incredibly precise experiments to measure Earth's motion through the ether as our planet orbited the Sunday. They set up interferometers that could detect changes in the speed of light so small that they were measuring effects thousands of times smaller than the width of a human hair, and they found nothing. No matter which direction they pointed their instruments, no matter what time of year they made their measurements, light always traveled at exactly the same speed. It was as if the ether didn't exist at all. This was completely Kanpai, baffling. How could light waves exist without any medium to carry them? It would be like having ocean waves with no ocean, sound waves with no air. The very foundation of 19th century physics was crumbling. Enter Albert Einstein, a 26-year-old patent clerk in Switzerland who had a very different way of thinking about these problems. In 1905, Einstein published a paper that didn't just solve the mystery of the missing ether, it completely redefined what space and time actually are. Einstein's insight was radical. There is no ether because space isn't empty. Space itself is a dynamic, flexible thing that can stretch and bend and curve. And time isn't a universal constant ticking away the same for everyone everywhere. Instead, space and time are woven together into a four-dimensional fabric called space-time. But here's where it gets really mind-bending. In Einstein's universe, the speed of light is absolute, but space and time are relative. If you're traveling very fast relative to someone else, time literally slows down for you. If you're in a strong gravitational field, space literally curves around you. Space and time aren't the fixed stage where physics happens. They're part of the physics itself. This completely changed how scientists thought about cosmic boundaries. Maybe the universe didn't need to have an edge in the traditional sense. Maybe space could curve back on itself like the surface of a sphere. Travel far enough in one direction, and you might find yourself approaching your starting point from the opposite direction. Einstein worked out the mathematical description of this curved space-time in his General Theory of Relativity, published in 1915. And when he applied his equations to the universe as a whole, he discovered something shocking. The universe couldn't be static. According to his own equations, space itself had to be either expanding or contracting. The cosmic fabric was dynamic, constantly changing. But Einstein couldn't accept this conclusion. Like Newton before him, he believed the universe had to be eternal and unchanging on the largest scales. So he added what he called a cosmological constant to his equations, a kind of anti-gravity force that would exactly balance the expansion or contraction and keep the universe static. Einstein would later call this the biggest mistake of his career, because in 1929, an American astronomer named Edwin Hubble made an observation that proved Einstein's original equations were right, and his cosmological constant was wrong. Hubble was using the most powerful telescope in the world, the 100-inch reflector on Mount Wilson in California, to study what astronomers called spiral nebulae, mysterious, fuzzy, spiral-shaped objects scattered across the night sky. Most astronomers thought these nebulae were just clouds of gas within our own Milky Way galaxy, but when Hubble measured the distances to these objects, he discovered they were incredibly far away, much too far to be part of our galaxy. These spiral nebulae weren't clouds of gas at all. They were entire galaxies, each one containing hundreds of billions of stars, scattered across vast distances through space. And then Hubble made an even more astonishing discovery. When he measured the light from these distant galaxies, he found that it was systematically shifted toward the red end of the spectrum. This red shift meant that every single galaxy was moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was expanding, not just growing by adding new matter at the edges, but actually stretching, with space itself getting bigger. Every galaxy was racing away from every other galaxy, carried apart by the expansion of space-time itself. Think about what this meant for cosmic boundaries. If the universe was expanding, then it had a history. You could run the expansion backwards and calculate when, everything was much closer together. Keep running it backwards, and you'd reach a point where all the matter and energy in the universe was compressed into an infinitely small, infinitely dense point. The universe had a beginning. About 14 billion years ago, space and time themselves came into existence in what would later be called the Big Bang. Before that moment, there was no before. There was no space for anything to exist in, no time for anything to happen in. But this raised new questions about cosmic boundaries that were even more puzzling than the old ones. If the universe had a beginning, did it also have an edge? When space expanded from that initial point, what was it expanding into? Was there some larger space that contained our expanding universe? Or was our universe creating space as it went? These questions led scientists to one of the most counterintuitive insights in modern physics. The universe might be both finite and unbounded at the same time. Just like the surface of a sphere is finite, you can calculate its exact area, but has no edge or boundary that you can reach. Imagine you're an ant crawling on the surface of a balloon that's being inflated. From your two-dimensional ant perspective, the surface is expanding. Any 2 points you mark on the balloon get farther apart as the balloon inflates. But the surface has no edge, no boundary you can crawl to. It's finite but unbounded. Our three-dimensional universe might work the same way, curved through some higher dimension we can't directly perceive. The universe could be finite in total volume, but still have no edge, no boundary, no place where space comes to an end. This possibility would have blown the minds of those ancient Babylonian priests or Greek philosophers. They were asking whether space had boundaries, and the answer might be yes and no, both and neither, depending on what you mean by boundary. But the expansion discovery raised an even deeper mystery. What was driving this expansion? What force was powerful enough to push galaxies apart across billions of light-years of space? Einstein's equations suggested that empty space itself might have energy, a kind of vacuum energy that could drive cosmic expansion. This idea seemed so strange that most physicists ignored it for decades. Empty space having energy? That was like saying nothing could do something, that the absence of matter could somehow push matter around. But in 1964, 2 radio engineers in New Jersey accidentally discovered proof that this cosmic expansion was real. Arno Penzias and Robert Wilson were trying to eliminate a persistent hiss from their radio antenna, a background noise that seemed to come from every direction in the sky, 24 hours a day. What they had found was the cosmic microwave background, radiation left over from the Big Bang itself. When the universe was very young and very hot, about 380,000 years after the Big Bang, it had cooled enough for the first atoms to form. Before that moment, space was filled with a hot plasma that was opaque to light. After that moment, space became transparent, and light could travel freely through the cosmos. That light has been traveling ever since, stretched by the expansion of space from visible wavelengths to microwaves. Penzias and Wilson were detecting the afterglow of creation itself, the universe's baby picture from when it was less than 400,000 years old. This discovery confirmed that the universe really did have a beginning, really was expanding, really did evolve from a hot, dense state billions of years ago. But it also revealed something profound about cosmic boundaries. We live inside the observable universe, a sphere about 93 billion light-years across, beyond which we simply cannot see, because light from farther away hasn't had time to reach us yet. The observable universe has a boundary, not an edge in space, but an edge in time. We can see back to when the universe became transparent, but no farther. Beyond that boundary lies the rest of the universe, whatever that might be. Is the universe infinite, beyond what we can observe? Is our Big Bang one of many, scattered through some larger cosmic space? Did the expansion start from a single point, or from infinite points simultaneously across infinite space? For the first time in human history, these questions about cosmic boundaries weren't just philosophical speculation. They were scientific hypotheses that could potentially be tested with observations and experiments. The revolution that began with Bruno's infinite cosmos and Galileo's telescope had culminated in the discovery that our universe is far stranger than anyone had ever imagined. Space and time are dynamic and flexible. The cosmos is expanding and evolving. We live in a bubble of observable space surrounded by regions we cannot see, in a universe that might be finite or infinite, bounded or unbounded, unique or one of countless others. The ancient question about the edge of space had become the modern question about the nature of existence itself, and the tools to answer that question were about to become more powerful than any cosmic investigator had ever dreamed possible. It's 1915, and Albert Einstein is sitting at his desk in Berlin, surrounded by sheets of paper covered in equations that look like hieroglyphics to anyone except a handful of theoretical physicists. He's been wrestling with the same problem for years: how to describe gravity not as a force, but as the curvature of space and time itself. And then, in a moment of mathematical insight that will reshape humanity's understanding of reality, Einstein writes down 10 interconnected equations that describe how matter and energy bend the fabric of space-time. These field equations are so elegant, so beautiful, that Einstein himself is almost afraid of their implications. Because when he applies these equations to the universe as a whole, they tell him something that contradicts everything he believes about cosmic stability. According to his own mathematics, the universe cannot be static. Space itself must be either expanding or contracting, like a vast four-dimensional balloon being inflated or deflated by some cosmic force. Einstein stares at these equations and refuses to believe them. The universe has to be eternal and unchanging. That's been the foundation of scientific thinking since Newton. So Einstein does something that he'll regret for the rest of his life. He adds an extra term to his equations, a cosmological constant that acts like a repulsive force, exactly balancing gravity to keep the universe static. But the mathematics won't be denied. Even with Einstein's cosmological constant, other physicists quickly realize that this cosmic balance is unstable. The Russian mathematician Alexander Friedmann and the Belgian physicist Georges Lemaitre independently discover that Einstein's modified equations still predict an evolving universe, one that's either expanding from a bold, primordial atom, as Lemaitre puts it, or contracting towards some future collapse. Meanwhile, half a world away, astronomers are building telescopes more powerful than anything humans have ever constructed. On Mount Wilson in California, the 100-inch Hooker telescope becomes operational in 1917. It's a monster, a mirror 8 feet across that can gather 4 times more light than any previous telescope. And the astronomer who gets to use this incredible machine is a former high school basketball player and boxer from Missouri named Edwin Hubble. Hubble has something that most astronomers of his era lack. He's equally comfortable with theoretical mathematics and hands-on observational work. He can spend all night at the telescope, carefully photographing faint objects, and then spend the next day analyzing those photographs with mathematical precision. In the early 1920s, Hubble turns the Hooker telescope toward the mysterious spiral nebulae that appear scattered across the night sky. Most astronomers think these fuzzy, spiral-shaped objects are just clouds of gas within our own Milky Way galaxy. But Hubble has a hunch that they're something much more extraordinary. Using a technique developed by the astronomer Henrietta Swan Leavitt, Hubble measures the distances to these spiral nebulae by finding Cepheid variable stars, FUS, stars that pulse with a regular rhythm that's directly related to their intrinsic brightness. It's like having cosmic lighthouses with known wattage scattered through space. By comparing how bright these stars appear versus how bright they actually are, Hubble can calculate exactly how far away they are, and the distances are staggering. These spiral nebulae aren't within our galaxy at all. They're entire galaxies themselves, each one containing hundreds of billions of stars, separated from us by millions of light-years of empty space. The Andromeda Spiral, the closest large galaxy to our own, is over 2 million light-years away. Think about what this means. For all of human history, when people looked up at the night sky, they were seeing our local cosmic neighborhood, stars within our own galaxy, maybe a few tens of thousands of light-years away at most. Suddenly, Hubble has revealed that the universe is filled with island universes, vast communities of stars scattered across distances so large that light takes millions of years to travel from one to another. But Hubble isn't done revolutionizing cosmology. In 1929, he makes an observation that will force Einstein to abandon his cosmological constant and embrace the expanding universe he tried so hard to avoid. Hubble measures not just the distances to these galaxies, but also their velocities, how fast they're moving toward or away from us. He does this by analyzing the spectrum of light from each galaxy, looking for the telltale signature of redshift or blueshift. Just like the Doppler effect makes an ambulance siren sound higher-pitched when it's approaching and lower-pitched when it's receding, light from moving galaxies gets shifted toward the blue end of the spectrum if they're approaching, or toward the red end if they're receding. What Hubble discovers is absolutely mind-blowing. Every single galaxy he observes, except for a few very close ones like Andromeda, is redshifted. Every galaxy in the universe is racing away from us. And here's the kicker. The farther away a galaxy is, the faster it's receding. Galaxies twice as far away are moving twice as fast. Galaxies 10 times as far away are moving 10 times as fast. This perfect correlation between distance and recession velocity can only mean one thing. The universe itself is expanding. It's not that galaxies are flying apart through space. It's that space itself is getting bigger, carrying the galaxies along with it, like raisins in a rising loaf of bread. When Einstein hears about Hubble's discovery, he travels to California to see the evidence for himself. He spends several days at Mount Wilson, looking through the Great Telescope, examining Hubble's photographs and calculations. And then he does something that takes extraordinary intellectual courage. He admits he was wrong. Einstein removes the cosmological constant from his equations and embraces the expanding universe. Later, he'll call the cosmological constant the biggest blunder of his career. The universe isn't static and eternal, it's dynamic and evolving, with a beginning in the finite past and an uncertain future. But this raises profound new questions about cosmic boundaries. If the universe is expanding, what is it expanding into? Is there some larger space that contains our expanding cosmos, or is our universe creating space as it grows? And here's an even stranger question. If you run the expansion backwards in time, all the galaxies get closer and closer together until you reach a moment when everything in the universe was compressed into a single point of infinite density and infinite temperature. How could such a state even exist? What happened at that moment to start the expansion? These questions push physics beyond the comfortable realm of everyday experience into territory that requires entirely new ways of thinking. And the answers will come from the most unlikely places, from tiny subatomic particles that exist for less than a billionth of a second, and from radiation so faint that it took the most sensitive instruments ever built to detect it. The first breakthrough comes in the 1940s and 50s, when physicists like George Gamow realized that the early universe must have been not just dense and hot, but hot enough for nuclear fusion to occur everywhere at once. In the first few minutes after the Big Bang, the entire universe was like the core of a star, with temperatures high enough to fuse hydrogen into helium. Gamow and his colleagues calculate exactly how much helium this cosmic furnace should have produced, and their prediction matches what astronomers observe in the universe today. About 25% helium, 75% hydrogen, with traces of other light elements. It's as if the entire cosmos still bears the chemical fingerprint of its violent birth. But Gamow makes an even bolder prediction. If the early universe was hot enough for nuclear fusion, it was also hot enough to emit intense electromagnetic radiation. As the universe expanded and cooled, this radiation should still be present, but stretched by cosmic expansion from high-energy gamma rays to low-energy microwaves. In other words, the universe should be glowing with the afterglow of its own creation. This cosmic microwave background radiation should be detectable everywhere in the sky, coming from every direction at once, with a temperature of just a few degrees above. Absolute zero. For nearly 20 years, astronomers search for this cosmic background radiation without success. The signal is predicted to be incredibly faint, easily overwhelmed by radio noise from Earth's atmosphere or even from the electronics of radio telescopes themselves. Then, in 1964, two radio engineers at Bell Telephone Laboratories in New Jersey stumble upon the discovery that will confirm the Big Bang Theory and open up an entirely new way of studying cosmic boundaries. Arno Penzias and Robert Wilson are trying to use a sensitive radio antenna to measure radio waves from space, but they keep detecting an annoying background hiss that seems to come from everywhere at once. They check their equipment, clean out pigeon droppings from the antenna, even build new electronics from scratch. But the hiss persists. Finally, they contact theoretical physicists at nearby Princeton University, who immediately recognize what Penzias and Wilson have found. The cosmic microwave background, the stretched and cooled radiation from the Big Bang itself. For the first time in human history, we're directly observing the universe as it was just 380,000 years after its birth, when it was still a glowing plasma cooling down enough for the first atoms to form. This discovery revolutionizes our understanding of cosmic boundaries in ways that nobody anticipated. The cosmic microwave background creates a kind of wall in time beyond which we cannot see. Before the universe became transparent at 380,000 years old, space was filled with hot plasma that scattered light in every direction. We can't see past this cosmic fog to the very beginning of time, but we can see right up to its edge. And this edge reveals something extraordinary about the shape and size of the observable universe. The cosmic microwave background shows us the most distant thing we can possibly observe, the surface of last scattering, where the light was first able to travel freely through space. This surface is now about 46 billion light-years away in every direction, creating a sphere of observability with us at the center. But here's what's truly mind-bending. This sphere is getting bigger every day. As time passes, light from more distant regions of the universe has time to reach us. The edge of the observable universe is constantly expanding, revealing new territories of space that were previously beyond our cosmic horizon. Yet at the same time, the galaxies we can see are being carried away from us by cosmic expansion. Some galaxies that we observe today will eventually disappear from view as they're carried beyond our observable horizon by the accelerating expansion of space. This creates a profound paradox about cosmic boundaries. We live at the center of an ever-expanding sphere of observability, but this sphere doesn't represent an edge in space, it represents an edge in time. Beyond the observable universe lies more universe, but it's universe we cannot see because light from those regions hasn't had time to reach us yet. How much more universe lies beyond what we can observe? Is the universe infinite, extending forever beyond our horizon, or is it finite but so large that we can only see a tiny fraction of the whole? These questions can't be answered by direct observation. Geo-observable universe is, by definition, all we can ever directly observe. But the cosmic microwave background gives us clues about cosmic boundaries in other ways. By studying tiny temperature fluctuations in this ancient radiation, astronomer, variations of just a few millionths of a degree, astronomers can map the geometry of space itself. If space is flat, like an infinite sheet of paper, then parallel light rays from distant objects should remain parallel as they travel to us. If space is curved like the surface of a sphere, then parallel light rays should converge slightly. If space is curved like a saddle, then parallel light rays should diverge. These different geometries predict different patterns in the cosmic microwave background, and when astronomers measure these patterns with exquisite precision, they discover something remarkable. Space is flat, or at least very close to flat, on the largest scales we can observe. This flatness has profound implications for cosmic boundaries. A flat universe can be either infinite in extent or finite but unbounded, like a cosmic torus or higher dimensional equivalent. But the observations can't tell us which of these possibilities is correct. They can only tell us about the geometry of space within our observable horizon. What lies beyond that horizon remains one of the deepest mysteries in science. The modern hunt for cosmic boundaries has revealed that the universe is far stranger and more complex than our ancestors ever imagined, but it has also shown us the fundamental limits of what we can ever hope to directly observe. The edge of space isn't a place we can travel to or see. It's a horizon in time that expands with every passing moment, always revealing new mysteries while hiding even greater ones beyond our reach. Here's where your mind needs to stretch in ways that might make you a little uncomfortable. We've discovered that the universe is expanding, that space itself is getting bigger every moment. But what does this expansion actually mean for the ultimate boundaries of existence? And more importantly, where is it all heading? Scientists have worked out three main scenarios for how this cosmic story could unfold, and each one paints a completely different picture of what reality actually is. Think of these as three different movies about the future of everything, each based on the same current evidence but leading to radically different endings. Let's start with the first possibility, and it's probably the one that would have made those ancient philosophers' heads spin the most. Infinite flatness, extending forever. Picture an endless sheet of paper stretching in every direction without any boundaries whatsoever. Now imagine that this paper represents space itself, and it's constantly getting bigger, not by adding new paper at the edges, there are no edges, but by stretching so that every point on the paper gets farther from every other point. In this scenario, the universe is what scientists call flat and infinite. Flat doesn't mean two-dimensional like an actual sheet of paper. It means that the geometry of space follows the same rules you learned in high school. Parallel lines never meet. The angles of a triangle always add up to 180 degrees, and if you shoot a laser beam in any direction, it will travel in a perfectly straight line forever. But here's what's absolutely mind-bending about this possibility. If space is truly infinite and flat, then somewhere out there, impossibly far away, there has to be an exact duplicate of you reading these exact words right now. I know that sounds completely crazy, but the mathematics is actually pretty straightforward. If space goes on forever, and if matter is distributed roughly evenly throughout that infinite space, then every possible arrangement of atoms will occur somewhere. And since the number of ways that atoms can be arranged within any finite region, say, a region the size of our observable universe, is large but not infinite, then these arrangements have to repeat. Think about it like this. If you have an infinite number of monkeys typing on an infinite number of typewriters, eventually one of them will type out the complete works of Shakespeare. In fact, infinitely many of them will type out Shakespeare, and infinitely many will type out every other book that's ever been written or ever could be written. In an infinite flat universe, those monkeys are atoms, and the typewriters are the laws of physics. Somewhere out there, perhaps 10 to the power of 10 to the power of 100, and 18 light years away, a distance so large that it doesn't fit into normal human language, there's another version of you living an identical life. There's also a version of you who decided to become an astronaut, a version who was born with purple hair, and infinite versions exploring every possible variation of what you could be. But let's talk about the expansion in this infinite flat scenario. Even though space is getting bigger, it doesn't mean the universe is growing into something else. There's no outside for it to expand into. Instead, space itself is stretching, carrying galaxies apart like dots drawn on a balloon that's being inflated. This expansion is driven by something called dark energy, which might be the strangest thing scientists have ever discovered. Dark energy appears to be a property of empty space itself. The more space there is, the more dark energy there is, pushing everything apart with ever-increasing force. In the infinite flat scenario, this expansion continues forever. Galaxies race apart at ever-increasing speeds until they disappear beyond each other's horizons. Stars burn out, black holes evaporate, and eventually, after an unimaginably long time, even protons themselves might decay, leaving nothing but a thin soup of elementary particles in an ever-expanding void. But remember, this is happening to infinite copies of our universe scattered throughout infinite space. So while our local region might fade into cold emptiness, infinite other regions are going through the same process, and infinite new structures might be forming in ways we can't predict. Now let's consider the second possibility. The universe curves like a cosmic sphere. This is actually easier to visualize than the infinite flat scenario, even though it's geometrically more complex. Imagine you're living on the surface of a sphere, not inside it, but on the two-dimensional surface itself. You can walk in any direction and never hit a wall or boundary, but if you walk far enough in a straight line, you'll eventually come back to where you started. In this scenario, our three-dimensional space works the same way, except it's curved through a fourth spatial dimension that we can't directly perceive. The universe is finite in volume. The first income, you could calculate exactly how much space it contains, but it has no edges or boundaries. Travel far enough in any direction, and you'd eventually see the back of your own head approaching from the opposite direction. This might sound impossible, but it's actually a natural solution to Einstein's equations. Space can curve back on itself, just like the surface of a sphere curves back on itself, except in higher dimensions. In fact, this closed universe model was one of the first cosmological solutions that scientists worked out from general relativity. The expansion in a closed universe is more complex than in the flat case. Early in cosmic history, dark energy might be weak enough that gravity dominates, and the expansion slows down over time. But if dark energy gets stronger, which observations suggest it does, then even a closed universe can expand forever, with the curvature getting flatter and flatter as space stretches. But here's where it gets really weird. In a closed universe, there might be multiple images of the same objects scattered across the sky. Light from a distant galaxy could travel all the way around the curved space and approach us from the opposite direction. If you had a powerful enough telescope, you might be able to see the Milky Way as it appeared billions of years ago, viewed from the far side of the universe. Even stranger, in some versions of closed universe models, time itself might be curved along with space. If the universe contracts after its current expansion phase, it might eventually collapse back to a big crunch that becomes the Big Bang of a new cycle. In this scenario, time would be circular, with the universe endlessly repeating the same cosmic evolution over and over again. Think about what this would mean for existence. Every moment you've ever experienced, every decision you've ever made, every thought you've ever had, all of it would happen again, exactly the same way in the next cosmic cycle. And it would have happened before, exactly the same way, in previous cycles stretching back through infinite time. But now we come to the third possibility, and this is where reality gets so strange that it challenges our basic concepts of what it means for something to exist. What if we live in one bubble among infinite bubbles in a vast multiverse foam? This scenario emerges from something called cosmic inflation theory, developed in the early 1980s by physicist Alan Guth. Inflation suggests that in the first tiny fraction of a second after the Big Bang, space expanded exponentially fast, erased much faster than it's expanding today. This rapid inflation stretched quantum fluctuations to cosmic scales, creating the seeds that eventually grew into galaxies and galaxy clusters. But here's the kicker. If inflation happened once, it's probably happening all the time, everywhere, creating infinite bubble universes in an ever-expanding multiverse foam. Our entire observable universe, everything we can see with our most powerful telescopes, might be just one tiny bubble in this vast cosmic foam. Each bubble universe could have completely different physics. In some bubbles, the fundamental constants might be different. Gravity might be stronger or weaker. The speed of light might be different. Matter might behave in ways we can't imagine. Some bubble universes might have 11 dimensions instead of our 4. Others might have no matter at all, just pure energy evolving according to laws of physics that don't exist in our universe. The space between these bubble universes, if you can even call it space, is constantly expanding and creating new bubbles. It's like a cosmic ocean where new islands of reality are constantly appearing, each one developing its own unique properties and evolution. And here's what's truly mind-bending. These bubble universes might occasionally collide. When two bubbles bump into each other, it could leave detectable traces, patterns in the cosmic microwave background that we could observe with our telescopes. Some scientists are actually looking for these collision signatures right now, scanning the sky for evidence that our universe has bumped into other universes. But the multiverse scenario raises profound questions about the nature of existence itself. If there are infinite bubble universes with every possible combination of physical laws and initial conditions, then everything that can exist does exist somewhere in the multiverse foam. There are universes where the laws of physics are so different that matter can't form. There are universes where stars never ignite. There are universes where life emerges in forms so alien that we couldn't recognize it as life at all. And yes, there are infinite universes where versions of you exist, but not just versions with different life choices. Versions where the fundamental laws of reality are different. Versions where time flows backwards, where effect precedes cause, where consciousness works in ways that are completely incomprehensible to our version of physics. So, which of these three scenarios is correct? The answer depends on the nature of dark energy, that mysterious force that's driving cosmic expansion. Current observations suggest that dark energy makes up about 68% of everything in the universe, but we have no idea what it actually is. If dark energy remains constant over time, then we're probably looking at scenario 1 or 2, either infinite flat expansion or curved expansion in a closed universe. But if dark energy changes over time, if it gets stronger or weaker or transforms into something else entirely, then scenario 3 becomes not just possible but likely. The same force that's pushing galaxies apart today could eventually tear apart molecules, atoms, even space and time themselves, creating conditions where new bubble universes could form. Recent observations from supernovae, galaxy surveys, and the cosmic microwave background suggest that dark energy is indeed changing, though very slowly. If this trend continues, it points toward an accelerating expansion that could eventually lead to what scientists call the Big Rip, a scenario where dark energy becomes so strong that it overcomes all other forces, tearing apart every structure in the universe and potentially creating the conditions for new bubble universes to form. But here's what's absolutely fascinating about these three scenarios. They all suggest that the question of cosmic boundaries isn't really about whether space has an edge. It's about the nature of existence itself. In the infinite flat scenario, existence is limitless but empty infinite space, with infinite possibilities, but no ultimate meaning or purpose beyond what we create for ourselves. In the closed scenario, existence is bounded, but eternal, finite space that might cycle endlessly through time, giving every moment infinite repetitions and infinite chances for every possibility to be explored. In the multiverse scenario, existence is both bounded and limitless, Our universe is finite, but it's embedded in an infinite foam of other universes, exploring every conceivable way that reality could work. Each scenario implies a completely different relationship between consciousness, meaning, and cosmic purpose. In an infinite universe, we're simultaneously unique and utterly common. In a closed universe, we're part of an eternal cycle that gives every moment cosmic significance. In a multiverse, we're part of an infinite exploration of what it means for anything to exist at all. And the remarkable thing is that we're living at the exact moment in cosmic history when we might be able to figure out which scenario is correct. The tools exist, the observations are being made, and the calculations are being refined. Within our lifetimes, we might finally answer the question that has haunted humanity since our ancestors first looked up at the stars and wondered where it all ends. The boundaries of space turn out to be inseparable from the boundaries of existence itself, and those boundaries are far stranger, far more wonderful, and far more profound than anyone ever imagined. You might be wondering why any of this matters. I mean, whether space has boundaries or goes on forever, whether we're in a flat universe or a curved one or a bubble in an infinite foam, none of that changes your daily life, right? You still have to get up tomorrow, go to work, pay your bills, figure out what to have for dinner. But here's the thing that's going to shift how you see everything. The shape of space determines the fate of everything that exists. And I mean everything. Every thought you've ever had, every person you've ever loved, every sunset you've ever watched, every moment of wonder or sadness or joy, the ultimate meaning and significance of all of it depends on which cosmic scenario we're actually living in. Let's start with something that sounds like pure science fiction, but is actually mathematical fact. If the universe is infinite, then somewhere out there, exactly copied down to the last atom, there's another you reading these exact words right now. This isn't just speculation. It's a direct consequence of what mathematicians call the pigeonhole principle applied to infinite space. In any finite region of space, there are only so many ways that atoms can be arranged. It's a huge number, something like 10 to the power of 10 to the power of 70 for a region the size of our observable universe. But it's still finite. If space is infinite and matter is distributed roughly evenly throughout that space, then every possible arrangement has to occur somewhere. And since the arrangements are finite but space is infinite, every arrangement has to occur infinitely many times. Think about what this means for your sense of uniqueness, your sense of importance, your understanding of what makes you, and you. Right now, there's another version of you who just decided to pause this story and go make a cup of coffee. There's a version who became a marine biologist and is diving in coral reefs. There's a version who never learned to read and is living a completely different kind of life. But more than that, there are versions where tiny differences in brain chemistry or life experience led to completely different personalities. There's a version of you who's incredibly brave where this version might be cautious. There's a version who finds different things funny, who falls in love with different people, who has completely different dreams and fears and hopes. If the universe is infinite, then the question, who am I, becomes, which version of me am I? And that fundamentally changes what it means to exist as an individual consciousness in an infinite cosmos. Now let's consider the opposite scenario, finite, closed universe that curves back on itself. In this case, you truly are unique. There's only one version of you, only one set of your thoughts and experiences, only one instance of your particular consciousness anywhere in all of reality. But this uniqueness comes with its own profound implications. In a closed universe, every moment matters in a way that's almost overwhelming to contemplate. Every decision you make, every word you speak, every act of kindness or cruelty, the only time. All of it is the only time that exact thing happens in the entire cosmos. And if the closed universe undergoes cycles of expansion and contraction, then your life, your thoughts, your experiences might repeat exactly over and over again through infinite cosmic cycles. Every time you've felt love, every time you've solved a problem, every time you've experienced that perfect moment when everything just clicks, all of those moments happen again and again, exactly the same way, forever. But what about the multiverse scenario? This one scrambles our concepts of existence in ways that are almost impossible to wrap your head around. If we live in one bubble among infinite bubbles, each with different laws of physics, then not only are there infinite versions of you, there are infinite versions of you living under completely different rules of reality. There are versions where time flows differently, where consciousness works in ways we can't imagine, where the very concept of identity might be fundamentally different from our experience. There might be versions of you that exist as patterns of pure energy, or as quantum processes that span multiple dimensions, or as forms of existence so alien that our language doesn't have words to describe them. And here's what's really wild. Some of these bubble universes might have physical constants tuned differently from ours. In our universe, if the strength of gravity or the nuclear forces were even slightly different, stars couldn't form, atoms would be unstable, and life as we know it would be impossible. But in a multiverse, there are bubbles where these constants are different, some where life is impossible, others where completely different forms of complexity and consciousness emerge. This raises what philosophers call the anthropic principle. We observe a universe with physical constants that allow for life and consciousness because we couldn't exist in universes where those constants are different. We're not special. We're just the inevitable result of infinite cosmic lottery drawings. But these aren't just abstract philosophical questions anymore. The shape of space, the nature of cosmic boundaries, the question of whether we're alone or part of infinite multiplicities, all of these directly affect technology and engineering that impacts your daily life right now. Your GPS system, for example, has to account for the curvature of space-time around Earth. Einstein's general relativity predicts that time runs slightly slower in stronger gravitational fields, and GPS satellites orbiting high above Earth experience time about 38 microseconds per day, faster than clocks on the surface. Without correcting for this relativistic effect, DPS, which comes directly from our understanding of curved spacetime, GPS would accumulate errors of about 6 miles per day. Every time you use your phone to navigate somewhere, you're relying on our understanding of how space and time are curved by mass and energy. The same mathematical principles that describe cosmic boundaries are what allow your GPS to pinpoint your location within a few feet. But the implications go much deeper than navigation systems. If we're planning future space missions beyond our solar system, e.g., missions that might take thousands of years to reach their destinations, we need to know whether space is flat or curved. In a flat universe, a spacecraft could travel in what appears to be a straight line forever. But in a closed universe, that same spacecraft might eventually loop back toward Earth, approaching from the opposite direction after traveling what seems like an infinite distance. The question of cosmic boundaries also touches the deepest levels of physics research happening right now. Scientists at the Large Hadron Collider in Europe are smashing particles together at energies approaching those that existed in the first fraction of a second after the Big Bang. They're looking for evidence of extra dimensions, for signatures of the multiverse, for clues about the fundamental structure of space-time itself. If they find evidence for extra dimensions, spatial dimensions beyond the 3 we experience directly, it could mean that our entire universe is like a thin membrane floating in a higher dimensional space. The boundaries of our space might be like the boundaries of a soap bubble film, 2-dimensional surfaces embedded in 3-dimensional reality. And some of the strangest predictions of modern physics suggest that these membrane universes could collide with each other, leaving detectable scars in the cosmic microwave background radiation. We might actually be able to observe evidence of other universes, other spaces with different physical laws, bumping into our cosmic bubble. There's another profound way that cosmic boundaries affect everything. They determine the ultimate fate of information itself. Every thought you think, every conversation you have, every book that's ever been written, all of it represents information patterns impressed into the physical structure of the universe. In an infinite flat universe expanding forever, this information gets diluted across ever-increasing volumes of space until it becomes undetectable. The conversations you're having today, the memories you're forming, the knowledge humanity is accumulating, all of it fades into cosmic background noise over unimaginably long timescales. But in a closed universe, information might be preserved forever. If space curves back on itself, if cosmic cycles repeat, then the information patterns that represent your consciousness, your memories, your experiences might persist through infinite iterations of cosmic evolution. And in a multiverse scenario, information takes on an almost mystical significance. Every possible pattern of information exists somewhere in the infinite foam of bubble universes. Every story that could be told, every thought that could be thought, every mathematical theorem that could be proved, all of it exists as actual physical reality somewhere in the multiverse. This isn't just affecting fundamental physics research either. Computer scientists working on quantum computing and artificial intelligence are grappling with questions about the nature of information and consciousness that directly relate to cosmic boundaries. If consciousness is an information pattern, and if the universe can generate infinite information patterns, then what does that mean for the possibility of artificial consciousness? For the preservation of human consciousness beyond biological death? For the ultimate meaning of thought and experience in a cosmic context? The edge of space is really the edge of everything we think we know about existence, consciousness, meaning, and purpose. It's not just about whether you could travel forever in a straight line. It's about whether your thoughts and experiences are unique treasures in a finite cosmos, or common occurrences in an infinite multiverse. It's about whether the person you love is the only version of them that will ever exist, or one of infinite variations exploring every possible way their consciousness could unfold. It's about whether the moments of beauty and wonder and connection you experience are rare, precious events in a bounded universe, or inevitable statistical outcomes in an infinite space of possibilities. Every atom in your body came from stars that lived and died billions of years ago. The carbon in your muscles, the iron in your blood, the calcium in your bones, all of it was forged in stellar furnaces and scattered through space when those stars exploded. You are, quite literally, made of stardust, but the ultimate fate of those atoms, and everything they might become in the far future, depends entirely on the shape and boundaries of space itself. In some cosmic scenarios, they'll be recycled through infinite future generations of stars and planets and life forms. In others, they'll fade into cold emptiness or be torn apart by accelerating expansion. In still others, they might be transformed into forms of matter and energy that operate according to completely different physical laws. The question of cosmic boundaries isn't abstract philosophy, one pow. It's the most practical question you could possibly ask about the nature of existence, because whether space has edges or extends forever determines whether your existence is a unique, irreplaceable event in cosmic history, or one iteration of infinite possibilities playing out across infinite realities. And that question changes everything about how you understand your place in the cosmos, your relationships with other people, your sense of meaning and purpose, and your understanding of what it truly means to be alive and conscious in this strange, beautiful, utterly mysterious universe we call home. Right now, as you're listening to this, there are 3 revolutionary experiments racing toward answers that could finally solve the mystery that has haunted humanity for 65,000 years. These aren't just incremental improvements in our telescopes or minor refinements in our mathematical models. These are breakthrough technologies that could fundamentally change our understanding of cosmic boundaries within the next few decades. And the incredible thing is, you're going to be here to see the answers. Let's start with something that's happening right this moment, 24 hours a day, 7 days a week, in the high deserts of Chile and on mountaintops around the world. The Dark Energy Survey has just finished mapping the positions and distances of over 500 million galaxies scattered across a quarter of the entire sky. 500 million galaxies. Think about that number for a second. Each one of those galaxies contains hundreds of billions of stars. Each star might have planets. Some of those planets might have life. We're mapping the three-dimensional structure of cosmic space on a scale that would have been completely incomprehensible to astronomers just a generation ago. But here's what makes this survey revolutionary. By measuring how galaxies are distributed through space, scientists can detect the subtle curvature of spacetime itself. If space is perfectly flat, galaxies should be arranged in patterns that follow the geometry you learned in school. But if space is curved, either like a sphere or like a saddle, then the galaxy distribution should show tiny but measurable deviations from flat geometry. The Dark Energy Survey is measuring these geometric distortions with unprecedented precision. We're talking about detecting curvature effects that change the apparent positions of galaxies by less than 1 part in 10,000. It's like measuring the curvature of Earth's surface by looking at how city lights are arranged when viewed from space, except we're doing it for the curvature of the entire universe. And the preliminary results are absolutely fascinating. Space appears to be either perfectly flat or so close to flat that our most sensitive instruments can't detect any curvature at all. This flatness is telling us something profound about cosmic boundaries. If the universe is flat and infinite, then the question isn't whether space has an edge. It's whether our specific region of space is typical of infinite space as a whole. But the Dark Energy Survey is just the beginning. In 2037, if everything goes according to plan, the European Space Agency will launch something that sounds like science fiction: the Laser Interferometer Space Antenna, or LISA. LISA will consist of 3 spacecraft flying in perfect formation, 2.5 million kilometers apart, farther apart than 6 times the distance from Earth to the Moon. These spacecraft will use laser beams to measure their distances from each other with such incredible precision that they can detect changes smaller than 1/10,000th the width of a proton. Why would anyone build such an impossibly sensitive instrument? Because LISA will be able to detect gravitational waves from the universe's first, second, ripples in spacetime itself, created when cosmic inflation first stretched quantum fluctuations to astronomical scales. These primordial gravitational waves carry information about the shape and boundaries of space that we simply cannot get any other way. They're like cosmic archaeologists that can tell us what happened before the universe became transparent to light, before the cosmic microwave background formed, right back to the moment when space and time themselves came into existence. And here's what's mind-blowing. If the multiverse theory is correct, these gravitational waves might carry signatures of other bubble universes. When bubble universes collide, they should create specific patterns of gravitational waves that LISA could detect. We might actually be able to observe evidence of other universes, other spaces with different physical laws, bumping into our cosmic bubble. But even LISA pales in comparison to what's being proposed for the mid-2040s, the hypertelescope. This isn't just a bigger version of current telescopes. It's a completely revolutionary approach to astronomy that could change our understanding of cosmic boundaries in ways we're just beginning to imagine. The hypertelescope would consist of multiple space-based telescopes flying in perfect coordination across distances of hundreds or thousands of kilometers. By combining the light from all these telescopes using a technique called interferometry, the hypertelescope would effectively create a single instrument with a resolution equivalent to a telescope the size of the entire formation. With this incredible resolution, the hypertelescope could do things that sound impossible. It could photograph the surfaces of planets around nearby stars in enough detail to detect continents and oceans. It could spot city lights on worlds hundreds of light years away. It could even search for signatures of advanced technological civilizations, patterns of energy use, or atmospheric composition that indicate intelligent life. But most importantly for our cosmic boundary quest, the hypertelescope could map the three-dimensional structure of space with such precision that it could detect even the tiniest deviations from perfect flatness. If space is curved on scales larger than our current observable universe, the hypertelescope might be able to detect that curvature by observing how distant galaxies appear, distorted relative to what we'd expect in perfectly flat space. And if the multiverse theory is correct, the hypertelescope might even be able to observe the collision signatures directly, scars in the cosmic microwave background where our universe has bumped into other bubble universes in the past. But the most revolutionary development isn't happening in space at all. It's happening in laboratories and computer centers around the world, where scientists are building quantum computers powerful enough to simulate the evolution of entire universes from their first moments. These aren't just faster versions of conventional computers. Quantum computers exploit the strange properties of quantum mechanics to perform calculations that would take conventional computers longer than the age of the universe to complete. And one of the most promising applications of quantum computing is cosmic simulation, HOA, creating virtual universes that evolve according to the same physical laws as our real universe. Within the next 20 years, quantum computers might become powerful enough to simulate the formation of cosmic structure from quantum fluctuations all the way up to galaxy formation and evolution. We could create thousands of virtual universes with slightly different initial conditions or physical constants and watch how they evolve. But here's where it gets really wild. Some of these simulations might be detailed enough to include the formation of stars, planets, and even life. We might be able to watch virtual civilizations evolve in simulated universes and see how different cosmic boundaries affect the development of intelligence and consciousness. And then there's Retit, the possibility that sends shivers down the spines of both physicists and philosophers. Within 50 years, we might create baby universes in laboratories. This isn't science fiction anymore. Theoretical physicists have worked out the mathematics for how cosmic inflation could be triggered artificially using incredibly powerful particle accelerators. By creating conditions similar to those that existed in the first fraction of a second after the Big Bang, we might be able to create tiny regions of space that undergo their own inflationary expansion. These laboratory universes would start smaller than atomic nuclei, but expand exponentially, potentially growing into full-sized cosmic spaces with their own galaxies, stars, and planets. They would be causally disconnected from our universe, for though cause foro, nothing that happens in the baby universe could affect our space, and nothing we do could affect the baby universe once it forms. But we could observe the formation process and watch these universes bubble off from our space, giving us direct observational evidence of how cosmic boundaries form and evolve. We might even be able to adjust the physical constants in these baby universes, creating spaces where gravity works differently, where time flows at different rates, where completely new forms of matter and energy could evolve. Think about what this means. The question that haunted those ancient Babylonian priests climbing their ziggurats, wondering what lay beyond the cosmic dome, will be answered by their descendants, Ayes, Per, who learned how to create new cosmic domes in laboratory experiments. But the biggest revolution might not come from new experiments at all. It might come from artificial intelligence systems that can process astronomical data and detect patterns that human scientists would never notice. Machine learning algorithms are already discovering new types of galaxies, new classes of stellar explosions, new patterns in the cosmic web of dark matter. As these AI systems become more sophisticated, they might identify signatures of cosmic boundaries that are invisible to human analysis. Imagine an AI system that can simultaneously analyze data from hundreds of different telescopes, space missions, and particle physics experiments, looking for correlations and patterns across all of cosmic physics. Such a system might detect subtle connections between quantum mechanics and cosmology that reveal the true nature of space and time on the largest scales. Or consider this possibility. An AI system might discover that the patterns we observe in the cosmic microwave background, the distribution of galaxies, and the behavior of dark energy are all connected in ways that point to specific models of cosmic boundaries. It might find that our universe shows subtle signatures of being a bubble in a larger multiverse foam, or evidence that space is curved in dimensions we can't directly perceive. The convergence of quantum computing, artificial intelligence, and next-generation astronomical instruments means we're approaching cosmic boundary questions with tools that are fundamentally more powerful than anything that's ever existed before. We're not just getting better telescopes, we're developing entirely new ways of thinking about space, time, and existence itself. And here's what's absolutely remarkable. Whether space ends or extends forever, whether we're alone or one of infinite versions, the journey to find out has made us more human, not less. Every ancient civilization that looked up at the stars and wondered about cosmic boundaries was really asking the same question we're asking today. What does it mean to exist? The Babylonian priests on their ziggurats, the Greek philosophers wrestling with infinite paradoxes, the astronomers who first glimpsed galaxies beyond our own, they were all trying to understand their place in the vastness. The tools have changed dramatically. We've gone from naked eye observations to space, telescopes, from geometric logic to quantum field theory, from mathematical speculation to laboratory universe creation. But the fundamental drive remains exactly the same. We want to know where we fit in the cosmic story. And that drive has led us to discoveries that have revolutionized human life in ways that go far beyond academic physics. The same insights that help us understand cosmic expansion have given us GPS systems, medical imaging technologies, and communication networks that span the globe. The mathematical tools we use to study space-time curvature are helping us develop quantum computers and artificial intelligence systems that will transform every aspect of human society. The search for cosmic boundaries has taught us that space and time are far stranger and more beautiful than our ancestors ever imagined. We've learned that we're made of elements forged in the hearts of stars, that our planet is a tiny oasis in a vast cosmic desert, that consciousness itself might be the rarest and most precious phenomenon in all of existence. But perhaps most importantly, we've learned that the capacity to ask questions about cosmic boundaries is itself one of the most remarkable features of the universe. Out of quantum fluctuations in the early cosmos, through billions of years of stellar evolution and planetary formation, life emerged that could contemplate its own existence. Consciousness arose that could wonder about the nature of space and time and cosmic purpose. Whether the universe is infinite or finite, whether we live in one cosmic bubble among many or in the only space that exists, whether our thoughts and experiences are unique events or common patterns repeated across infinite realities, none of that changes the fundamental miracle that we're here at all. Asking these questions, capable of wonder and discovery and love. The edge of space, whatever it turns out to be, is also the edge of human possibility. Every boundary we discover teaches us something new about what it means to be conscious beings in a cosmos that's vast beyond imagination. Every answer we find opens up new questions that push the limits of what minds like ours can comprehend. And the most beautiful part is that this journey of discovery is just beginning. The questions that have driven human curiosity for thousands of generations are about to be answered by technologies that seem almost magical compared to what our ancestors had to work with. Within your lifetime, we'll know whether space has boundaries or extends forever. We'll understand whether we're alone in our cosmic bubble or part of an infinite multiverse foam. We'll discover whether consciousness is a rare accident or an inevitable feature of cosmic evolution. The ancient wonder that drove humans to climb ziggurats and build telescopes and launch space missions has brought us to the threshold of answering the deepest questions about existence itself. And whatever those answers turn out to be, they'll be discovered by the descendants of apes who learned to look up at the stars and wonder what was out there beyond the farthest thing they could see. That journey from wonder to understanding, from questions to answers, from the edge of ignorance to the edge of cosmic knowledge. That's what makes us human. And that journey has just begun.